We are talking in general terms, this sort of topic that we started last time and are going to continue this time and probably next time also, is about closure properties. I didn't use these words to describe it last time, but closure properties for regular languages. Closure properties. I'm going to close the door. Closure, the word closure is being used in the sense of, like, if you recall in linear algebra, you said, for example, a subspace is closed under addition. What that means is if I add two things in the subspace, the sum is also in the subspace. Closure means sort of, if I got something which is one of those things, and I combine them in some way, the answer is, again, one of those things. That's what the word closure generally means. Or like if you took the abstract algebra, you use this word a lot about something is closed under multiplication, something like that. Closure properties for regular languages means if I have two regular languages and I combine them in a certain way, I get another regular language. That's the basic idea. Although the only one that we've talked about so far has been the complement, but it says, if L is a regular language, and remember what that means is it is a language which can be the language accepted by a DFA, right? And what we talked about at the end last time was if L is a regular language, then L bar, the complement, is also a regular language. And my goal for today is to talk about unions and intersections. So we're also going to talk about if L1 and L2 are regular languages, then the intersection is also a regular language, or then the union is also a regular language. That's the kind of thing that we want to talk about. In terms of like phrasing it like a closure property, I would say for this particular thing, the regular languages are closed under complement. That means if you start with a regular language and you take the complement, the result is again a regular language. All right, closed under complements. And each of these closure properties carries with it a particular construction for DFAs. So for if we have a DFA, for L, how do you get a DFA for L bar, the complement? The DFA for L bar is obtained by, anybody remember? Yeah.
Swapping the accepting and rejecting.
Right, you sort of reverse every state. All the rejecting states become accepting states, and all the accepting states become rejecting states. So the DFA for L bar, otherwise it's the same. You use the same states, the same arrows, same everything. It's just you swap accepting versus rejecting. If we have a DFA for L, the DFA for L bar is obtained by, I'm going to try and say what I just said, swapping all accepting / rejecting states. All right? And that's very simple to do, right? You can immediately do this. This is the closure property for complements. Today I want to talk about the closure property for intersections. And this is quite a bit more complicated. Intersections. All right, so in terms of languages, what I want to talk about is if L1 and L2 are regular languages, two different regular languages, then this is actually a true fact. Maybe I'll write this as a theorem, although we're not going to. For now, I'm just telling you, but we will eventually discuss exactly why this is true. But it is a fact. If L1 and L2 are regular languages, then L1 intersect L2 is a regular language. All right. This intersection, of course, means all strings which are from L1 and also in L2, right? That's the intersection, sort of logically speaking, has the meaning of the word and. So things which are in L1 and L2. All right. Most of what I want to talk about is a construction for DFAs. So from the point of view of DFAs, what this represents is I have two different DFAs, one with the first language and one with the second language, and I want to somehow combine them into one DFA which has the intersection as the language. And on DFAs, the name of this, it's much more complicated than just swapping, accepting, rejecting states. That is so simple that it doesn't really have a name. There's a name for the construction that you do on the machine. This is done using what's called the product construction. And you'll see why it's called a product once we talk about it a little bit. I thought we'd start by just doing an example of the product construction. And then we'll go back and see why exactly it works. I mean, that's the theorem that I wrote there. If you wanted a proof of the theorem, why is it that L1 intersect L2 is a regular language? Well, it has to do with this particular construction. So here's an example just to demonstrate. Let's say in this example, just to make everything simple, my alphabet is just a single letter. Sigma equals just A. And let's say our first language, L1, is the set of all A to the n where n is even. And L2 is the set of all A to the n where n is divisible by 3. These are just two simple examples of DFAs. Or simple examples of regular languages. But they each come from a DFA, right? So maybe I'll write what those two DFAs would be. M1 is my DFA for the first language. A DFA that accepts only when n is even. That's sort of like a back and forth two-state kind of thing. And just for emphasis, I know this is simple, but because of what I'm going to say, I'm going to name these two states. It's a matter of evens and odds, right? And I go like that, and this is my starting state. So that's my first machine, which accepts any A to the n where n is even. My second machine, n is divisible by 3. Anybody remember how to do that?
Did you need 3 states?
Yeah, 3 states kind of going in a circle.
Mm-hmm.
So I'll call this one M2. This will be the machine which accepts, it's going to be like this, right? And rather than saying evens and odds, really it means sort of the starting state is like when the number is 0 mod 3, or when it's 1 mod 3, or when it's 2 mod 3. Can I just call these 0, 1, and 2? That means, these are all A's, the arrows. So something in this state is equal to 0 mod 3, that is, it is divisible by 3. Something over here is 1 mod 3. Something down here is 2 mod 3. Emergency. All right. Well, look at this. I labeled my starting arrow here. That doesn't make any sense. Sorry, that's bogus. All right. Okay, what I want to do is somehow combine the two pictures into some big machine which accepts when it's even and also divisible by 3, right? That's what I want. So we want to combine everything, combine these two. I will say this kind of informally, with and, right? You want to make a machine which does the same stuff but accepts only when both of those original two machines are accepting, all right? That's what I mean by and. It has to be acceptable on the first one and also on the second one. And the way to do this is we combine the states in pairs. So I'm going to make a new machine, which is going to be bigger, quite a lot bigger actually, where each state of the new machine is a pair of states from the original machine. So my original machine had even and odd, and my second one had 0, 1, 2, 3. No, 0, 1, 2, right? So the new states are going to be even paired with 0. That's a state. Even paired with 1. That's a state. Even paired with 2. That's a state. All right? And then similarly for odd. So I have a total of 6 states in this machine. Odd and 0 mod 3. Odd and 1 mod 3. Odd and 2 mod 3. All right? 6 states. So the states, I'm going to try and do a little narration here. The states are pairs of states from the original machine. From the original machines. All right. How do we draw in the arrows? Well, we are going to draw the arrows. Let's say, look at this one, starting even and 0. You have to, I don't think I can hold it all on the screen at once. Maybe if I scroll it out. Yeah, that's all right. Starting even and 0, what I do to say, where's the arrow? Well, the alphabet here is still going to be just A. So all of my arrows are going to be labeled with A's. Where does this one go if you do an A? You got to look on each of the 2 machines up there and say where each of them goes. So on M1, if I do an A from even, it becomes odd. And from 0, it becomes 1. So I do both of those down here. Even and 0. The even becomes an odd. The 0 becomes a 1. So even and 0 goes to odd and 1. All right? The idea is this machine down at the bottom is a combination of both of the machines on top, doing them sort of simultaneously. Everything is happening at the same time. If it's an even, it goes to odd. If it's a 0, it goes to 1. You just do them at the same time. And then I'm just going to draw in arrows everywhere with that same method. I only have to draw A, so it's not so difficult. How about this? From even comma 1, can somebody say where should the arrow go to? Yeah, what do you think? Odd comma 2. Yeah, because even goes to odd up here, and 1 goes to 2 over here. So this goes like that. Now some of my arrows are going to cross over, unfortunately. Even and 2 goes to odd and 1, right? Because 2 goes, 0. Even and 2 goes to odd and 0. I'm going to have to cross the streams a little. Even and 2 goes to odd and 0. And so on. You should fill in, I guess, 6 total arrows here, right? Over here, odd and 0 should go to even and 1. That's like that. Odd and 1 should go to even and 2, like that. And odd and 2 should go back to even and 0, like that. It's a little confusing. Yes?
Okay, they have different languages. Like if you want to L1 and L2, do they have to have the same language?
They have to use the same alphabet letters. That's what you mean. Yeah, because I intend to, the whole point of this is I want to look at L1 intersect L2, right? If they were using totally different alphabets, then this would be nothing, or the empty set. So you wouldn't even do this in that case. Yeah. All right. Great. This is how we do it. We combine the states in pairs. Now, we should also say what's the starting state? What do you think? Anybody have? Yeah, even and 0. If you think about the point of this, it's supposed to be some kind of combination of those 2 diagrams. And so you locate the starting state on each of these 2 here and here, and that's where the starting state goes down here. All right. And then which ones should be accepting? Remember, the purpose of this DFA that I'm drawing at the bottom is to get the intersection. I want to accept things which are accepted on M1 and also on M2. What do you think?
Just be even and 0 again.
Yeah, just even and 0. And why did you say that?
Because that's the only accepting state in both the other machines.
Right, because I'm supposed to take accepting here and also accepting here. The only way to do that in this particular example is even and 0. All right, so the accepting states here let me just finish saying. So the states are pairs of states from the original machine. I will just say the transitions apply the letter to each part of the pair. I don't know if that makes sense. I hope that it makes sense what I'm trying to say there. The way, for instance, I figured out where does odd and 0 go is I said, where does the odd go, first of all, and separately, where does the 0 go? And then you draw the line from there. The transitions, you do whatever you do to each part of the pair. The starting state is just the pair that you get from taking the two original starting states. So the starting state is the pair obtained from the starting state of M1 and M2, right? And the accepting state is any state which was accepting, any pair which is made up of two accepting states, right? Both parts of the pair are accepting in the original machine. So accepting states. Now in the example that I just did, there was only one, but there could be more than one. Accepting states are any pair of states which are both accepting in M1 and M2. All right? This is how we do the product construction. All right? And I hope it's clear by what we did. This is going to accept any string of A's which is even length and the length is divisible by 3. All right? You could also, by the way, I drew this diagram with a lot of crossovers. You can actually untangle this diagram and it looks like, I'm just going to do it down here. Our example is equivalent to this. You can actually arrange them all in a circle. Right, there were 6 states. One of them was an accepting state, and actually, if you look at that one with a bunch of crossing over arrows, if I ignore the labels, actually, you can unravel everything, and it looks like that. Does that look like anything? Anybody feel good about that? I mean, sure, it looks like something, but
It has to be like divisible by 6.
yeah, this means the thing is going to be divisible by 6. And if you think about it, that is exactly what it means to say it's even length and also divisible by 3. That means it has to be divisible by 6. So this makes a lot of sense that diagram we ended up with actually looks like this. And, you know, even if you didn't know anything about this construction, you might have come up with this, you know, just by reasoning out the fact that if it's even length and divisible by 3, it has to be divisible by 6, and so it should look like that. So that actually is what we expect to come up with as the answer. All right? I thought maybe we should all try an example. I'm going to give you 2 DFAs. Your job is to combine them together into a DFA which accepts the intersection. And for fun, let's make this one have more than just one letter. Let's try this. So let's say that's my M1, my first DFA. And then let's say my M2 is how about this is not very interesting, sorry. Let's do that. I'm done now. All right, make a machine for the intersection. How about this? I'll get us started. Let's give names to all the states just to help us keep it straight. So from the first DFA, maybe I'll call them S and T, and the second one I'll call U, V, and W in that order. All right. And my product machine is going to have pairs where the first thing is either S or T, and the second thing is a U, a V, or a W. So maybe I'll put the S's across the top. It's going to say SU, that's one pair. SV, SW, and then I got TU, TV, and TW. And let's draw the arrows, and then I'll just draw the first arrows from SU, okay? We need an A and a B, because my alphabet in this case is A's and B's. Where does the A go from SU? You look at up here, where does the A go from S? It goes back to S. And where does the A go from U? It goes to V. So SU goes to SV with the A. And then where does the B go from SU? Again, you look up top, where the B goes, where the B goes. From S, the B goes to T. From U, the B goes to W. So SU goes to TW with a B, like that. All right. So see if you can put in all the other arrows, and then also decide where the starting state is, and also decide where the accepting states are. I'll give you a moment. I'll walk around and see how everybody's doing. I'm going to do mine slowly up here. Don't let me ruin the fun for you. All right, let's talk about these. I did some of them. I hope I didn't mess any up. Did I mess them up?
I think.
Give me bad looks.
TW.
TW?
I think it goes to TB. B goes to T.
I like that as well.
Yeah.
I got that too.
Like the TW, the arrow that's going from TW
The
to
B.
SV, the B.
B.
It's a
Yes,
B.
yes. Oh, okay, so it should go straight across on the bottom, not up. Is that what you mean? Here?
Yeah.
Yes, thank you. These are easy to mess up, as you can see. I hope you gotta kind of look carefully and draw in the arrows. I hope that you were able to draw the arrows. Now, I actually didn't write any arrows coming out of S, W, or TU. It's because I think if you did it correctly, and if I did it correctly, those states are actually not necessary to include in the diagram. Anybody see why not? Why not?
You cannot reach there.
Yeah, they are actually unreachable from the starting state. The starting state in this case is S comma U, which is here, right? And if you put in the arrows from here and also from here, they don't contribute to the diagram in the sense that if you start here, these are the only 4 states you can ever arrive at, right? There's no way to get to these guys from the rest of the diagram. So in fact, in this, now it's not wrong if you drew the whole thing in, but it's not necessary. In this case, these guys are unreachable. So let me just say, some pairs may be unreachable from the starting state. And in that case, you might as well leave them out.
Are you just going to draw them in, or can you just not draw them at all?
Yeah, you can just not draw them at all if you don't want to. And in fact, now I started this off trying to emphasize the pairwise structure here, but actually, if you want to do this in the most efficient way, what I would expect, or what I would suggest in this example, would be you start off drawing the starting state, which is S comma U. And I think as I was going around, I saw a couple people maybe did this. And now, rather than drawing this whole grid of all 6 states, I'm just only going to draw the ones that I can actually reach. This is similar to what I did with the farmer going across the river thing. We just started from each one, and we only drew the ones that we can get to. So from SU, if I do an A, I go to SV. And if I do a B, I go somewhere else, which I'll just put down here. TW, right? This is a A, this is a B, etc. Right? Making no effort to put them in that 2x3 grid. You just put them wherever they fit, wherever is most convenient for them to fit in. All right. So some pairs may be unreachable from the starting state. If you're trying to save yourself some heartache, like with these, it's not such a big deal to write down all the pairs. There's only 6 of them. But if you started with larger DFAs, you probably only want to draw the reachable states because there's just going to be lots more extra ones. You want to save yourself some work. All right. Anyway, can we just? I'll just do it on this one. Which ones are accepting states here? TV is accepting, yes, and also TU is accepting, although it's unreachable, so it doesn't matter. But this is an accepting state, and I would say I'll just do that just to make it clear. TU should have also been an accepting state because those are the pairs which are both accepting in both coordinates, right? T comma V, both T and V are accepting in the original one. T comma U also, both T and U are accepting in the original 2 machines. All right? And the reason I want both is because we're talking about the intersection, which as far as sets goes is and, right? It's in this set and also this set. That's why I'm taking pairs in which both are accepting. All right? Great. Let's talk. We got about 15 minutes. I would like to actually prove that this works. So can we prove... This is what our book refers to as prove the product construction. Product construction. Prove that it really works. When you combine 2 DFAs in this way that I described, the language of the result is the intersection of the 2 original languages. I'm not sure if we can do this in our remaining 16 minutes, but we'll start on the journey at least. All right, now to prove things about DFA, remember you need to use that formalized description. And so I'm going to try to write everything formalistically. So let's say that M1 is a DFA given by this. Remember, a DFA is this 5-tuple thing. Actually, I'm going to say just Q. I'll call them different, slightly different things. And M2, I will say, is R sigma. They have to have the same alphabet or else you don't even try to talk about the intersection. Delta, I'm going to call this delta 2, R naught, and F0. All right. These are two DFAs. Remember what each of those ingredients represents. The first thing is the set of states. The second thing is the alphabet, which has to be the same for your two DFAs. The third thing, the deltas, are the transition functions, which describe the arrows. The fourth thing are the starting states, and the last part is the set of accepting states. Then, let's say those are my two DFAs. Then, when you do the product construction, it results in... Can we describe formally what the result is? I'll call it M3. It's another machine. Yeah.
Did we say F0 or F2?
Oh yeah, I meant F2. Thanks. Yeah, it doesn't make sense. I suppose it's not illegal, but you might as well. F1 and F2. Thank you for that. All right, what is the result of the product construction? So what we have to think about is, if I start with the first machine had the states were Q, the second machine the states were R. What are the states in the product? They are made up of pairs.
Q cross R.
Yeah, this would be Q cross R. Hope you remember your set theory. Q cross R means the set of all pairs where the first thing comes from Q and the second thing comes from R. That is exactly what we want for the states of the product machine. Okay, what is the alphabet used on the product machine? It's also sigma. It's the same alphabet. It was still A's and B's or whatever. So no funny business on the sigma. Now the delta is going to be a little complicated. So can I just write delta here, and then down there I'm going to say where delta. I will describe what delta is later on, just because that's always the most complicated part. What about the starting state? Yeah, the starting state, remember in this machine M3, the states are all pairs. And so what I put here should be a pair. And what it is, we talked about. How do you find the starting state in the pair? It's just the pair of the original two starting states. That would be Q0, R0. So that's the starting state of the product machine. And what is the set of accepting states in the product? It's all the pairs where the first one was accepting and also the second one was accepting. How can we write that here? Not quite. Oh, that's a good idea, just because the goal of everything we're talking about is to get intersections, but actually, what I need to describe here is a subset of that, right? So whatever it is has to be made up of pairs. What do you think? No, that's what she said.
F1 cross F2.
F1 cross F2, yes. Thank you. F1 cross F2, right? This would be the set of all pairs where the first thing is in F1 and the second thing is in F2. That's exactly what we want. The first part of the pair is accepting and the second part of the pair is accepting. Great. Okay, so that's what the product machine is as a set. Yeah.
Do we have to put in like set distance as the set of the accepting states, or just because it's the one you don't want to?
You mean should we wrap this inside like that?
Yeah.
We should not. Actually, we should keep it this way. Come on. Oops. When you put the product, it means this is a set of all pairs. If you put an additional bracket around it, that's too many brackets. That means the set containing the set of all pairs, which is not what we want. Yeah. Great. Anybody wondering, should we put the star somewhere? No. Some people's approach to the star on the homework was like, I'll just put the star sometimes I won't, whatever. The star really does mean something. It is a little confusing, but the star belongs nowhere here. The star makes things into strings. You might consider putting the star here, just because, like, if the star is going to go anywhere, sometimes we put it on the sigma, but not in this case. In this position, the sigma represents the alphabet, not the set of all the strings. So no star there. Okay, we got to say, what is delta now? Delta is a function. Remember, the way the function works is what goes into it is a pair of a state, comma, a letter. So what I'm going to put here is a state in M3, though, itself is a pair. So really what the delta this time looks like is something like this. Because usually what you plug into the delta is a pair, a state, comma, a letter. But in this particular machine, the states themselves are also pairs, so it looks a little more complicated. But anyway, how do you decide what is the answer if I plug into delta here? The answer here should be a state, which is a pair. How do you get the answer? You basically get it by, if you recall, how did you decide where to draw these arrows? You look on the two original states and you kind of do each of the transitions on each part of the pair. Does anybody see how could we write that down here? This says if I start in the pair QR and I read the letter A, what should I go to?
Delta of Q A, comma, delta of Q R.
Yes. So it should say delta 1 QA, comma, delta 2 RA. I'm using delta 1 and delta 2. Delta 1, remember, is the function describing the arrows from the first machine. Delta 2 is the function describing the arrows from the second machine. And so this is how we do the delta on the big machine. It is just doing the deltas, the original two deltas in each pair. Excellent. All right. So this is the machine that we get when we do the product construction. And our proof, what I said, we're trying to prove that this is correct. So our proof should show that the whole point of this, remember, is that the language of the product machine is the intersection of the other two languages. So our proof should show that the language of M3 is the intersection, language of M1, intersect, language of M2. That's the whole point of the product construction. The reason we're doing this is that the language of the big machine is supposed to be the intersection of the other two languages. And can we prove that? Actually, this is not so hard to prove. You just have to write a bunch of set theory, but once we've set the whole thing up, everything is going to work out very nicely. Actually, before I start writing the proof, I will just refresh our memory. This is a little parenthetical. Remember, what's the set theory definition of L of M, the language of a machine? Does anyone remember this? It was slightly complicated. Yeah.
Is it like X is any string that, and then
Yeah.
there's a delta thing in there?
There's a delta thing. Yeah. Anyone remember what it was? It's a set of all strings such that. See, some people are turning back. Turn back the hands of
X
time.
is not in.
Delta star, I think.
Mm-hmm. Yeah.
Q naught, comma X is in there.
Yeah. This is the definition, as far as the set theory goes, of the language accepted by a machine M. This stuff on the right side here, remember what that means? It means if I start in state Q naught, which is the starting state, and I do this whole string X, the delta star, remember, means it's the same as the delta, only it does many steps at once, the whole string. It ends up being in the set of accepting states. All right. So our proof is going to show that those two sets up there are equal. So let's see if we can do this. Proof. I'm just going to start on one side of the equal sign and try to rewrite, resimplify until I get the thing on the other side. Let's start on the left side. L of M equals. The whole proof is really just going to be a bunch of equalities where we rewrite the set and eventually end up with what we're looking for, the intersection. M3 is what I see on the left-hand side. Okay, what is it? It is the set X in sigma star such that. Now this delta star, we call delta star, right? You can just say delta star of. Now, what you see in red there is Q0. That's the starting state. When I'm talking about M3, the starting state is actually Q0 comma R0. So that goes here. Comma X. And I have to show this is in. Instead of that F there, I want the set of accepting states for M3, which we set up here was at the very top there, F1 cross F2. So right here has to be an element of F1 cross F2. All right. And now, everything we've done so far, the set theory just kind of works itself out. All we have to do is rewrite this stuff. So one step I'm going to do is, what is delta star of that? Well, we said up here what delta is. You can see it right at the top right there. Delta of something something is delta 1 of the first thing, comma, delta 2 of the second thing. So this, the same will be true of the stars. So this is the pair, delta star 1, or delta 1 star, whatever you want to say, Q0x, comma, delta 2 star, R0x, right? And then I'm writing the same stuff is in F1 cross F2. So all I did there was I replaced the delta star with this pair. That's because the delta of this stuff equals that stuff. And we just plugged it in exactly like that down here. The only difference is the, I wrote A up here, represent a single letter, but down here I wrote X for any possibly long string. All right? Okay, what else? We got 4 minutes. That's plenty of time. Let's simplify again. Another way to say this. Now, I want to eventually end up with an intersection, so I would like at some point to logically introduce the word and, right? Because the answer is supposed to involve an intersection of something. How can I say this in terms of the word and? Right here, what it says is this pair is in this set of pairs. Remember what that set means? It means the set of all things where the first thing is in F1 and the second thing is in F2. And so I'm going to rewrite this by saying this first thing is in F1 and the second thing is in F2. That's what it means for this pair to be part of that product set. So this means delta 1 star Q0x is in F1. And if you want to look real fancy, you can write the little wedgie thing that means and. I'm not trying to impress anybody though. I'm very secure in my masculinity. I don't need to use unnecessary symbols to impress people. I'm a happily married man. All right? This is the beginning of our journey towards the intersection. And actually, this is kind of the end. We can immediately express this then as an intersection of two sets. It's the set of which has that first thing, intersection with the set of that second thing. So this, writing as an intersection, is X in sigma star such that delta 1 star Q0x is in F1. Intersection X in sigma star such that delta 2 star R0x is in F2. All right? Because that's what the word and means. Or that's what the intersection means. And then what are each of those sets? Anybody see where we're going with this? Actually, that first set is, it is L of M1, right? That's the language accepted by M1. You can still kind of see it at the top, what the L means, right? It means exactly what you see down there. This is L of M1, intersect L of M2. The end. That's what we wanted, all right? The set theory actually helps. You know, it allows you, I don't know if you are really into set theory, and you might it's kind of intimidating to see it written in this way, but it allows you to write a proof like that having essentially no big ideas, right? You just have to rewrite things and everything works out great. That's the beauty of using the set theory, is that if you set it all up properly to begin with, the proof kind of works out on its own without you having to have any kind of creative ideas. All right, I think that'll do for now. Next time we'll talk about unions.